Hello everyone, my name is Dr. Neil Shenvi and I am talking to you tonight about miracles, materialism, and quantum mechanics. I'm a research scientist in the Department of Chemistry in Duke University. I work right over in the French Sciences building, and quantum mechanics has been my professional area of expertise for about 10 years now, and it's also a beautiful subject. I really love it, and I hope I can convey some of my enthusiasm for quantum mechanics to you tonight. Let's begin with my outline. I want to begin by framing the talk with some questions about the nature of reality itself. We often make many assumptions about the nature of reality, and we don't often realize we're making them. I want to say that quantum mechanics challenges many of our ideas about the nature of reality, and I want to think about this talk in light of those questions. I'll then spend the bulk of this talk discussing quantum mechanics itself. What's the history of quantum mechanics? What are the fundamental postulates of quantum mechanics? I'll skip the part about the experimental verification of quantum mechanics. Suffice it to say that quantum mechanics has been verified to a tremendous level of detail, more than any other theory of physics in history. In part 5, I'll discuss the three major interpretations of quantum mechanics, and then I'll tease out their philosophical implications in part 6, and then I'll tie this all back to the questions we asked initially about the fundamental assumptions we make about the nature of reality. So let's begin by asking these questions. The scientific endeavor requires us to make many assumptions about the very nature of reality. For instance, to even engage in science, we need to assume that the universe is rational, and that, in particular, it's accessible to human reason. If it's not, then why even do science? It's impossible. We also have to assume that there is a universe that exists objectively, apart from human experience. We have to assume things about causality, about spatial regularity and temporal regularity, that measurements we make here are the same elsewhere in the universe, things like that. And all of these presuppositions are required for us to even do science. But we can also speak a little bit more personally. All of us make fundamental presuppositions about the nature of reality on a daily basis. Now I want to look at some of the fundamental assumptions we might make if we're naturalists. A naturalist is someone who denies that any supernatural realm outside or beyond nature exists. I'm not saying that all naturalists will hold to these assumptions, but I think they'll be familiar to many naturalists. For instance, we might believe that the laws of physics state that miracles are impossible. They cannot happen. Second, we might say that even if God does exist, well, he could not be a God who intervenes in the natural world, because then he'd have to violate the physical laws that he himself supposedly created, and that would just be sloppy. Third, we might believe that there is no mind or consciousness that is separate from physical constituents. In that sense, mind is simply a collective property of matter in the same way that wetness is a collective property of molecules of water. Finally, we might believe that the universe does not contain hidden or unknowable realities that are inaccessible to science or observation. The question is, are these assumptions plausible? And I want to ask whether or not quantum physics actually challenges many of these naive assumptions that we often make if we're a naturalist. So let's look now at the history of quantum mechanics. We're all familiar with Newtonian or classical mechanics. If we've taken high school physics, we're familiar with the three laws of motion under Newtonian mechanics. And even if we haven't, we're familiar with Newtonian mechanics because it simply describes the motion of everyday objects, objects like cars, anvils, and basketballs. And Newtonian mechanics reigned supreme in physics for over 200 years. It was remarkably successful. It described the motion of planets. It enabled us to build machines like clocks and trains. And a tremendous amount of physics was built upon this Newtonian foundation. But around the turn of the century, there were a few experiments that really defied explanation by recourse to classical Newtonian explanations. People tried very hard, but they were stones in the shoes of 20th century physicists. And then something very remarkable happened. Around the 1900s, the early 1900s, an entirely new paradigm of physics developed, and that was quantum mechanics. This began in 1900 with the introduction of Planck's constant by Max Planck, and then it continued for about 3 or 4 decades. The foundations of quantum mechanics were really established during these early years, and they have remained unchanged, even though quantum mechanics is over 100 years old now. Although we've grown to know much more about the implications of and applications of quantum mechanics, and indeed we've grown to appreciate how unintuitive quantum mechanics actually is, the fundamental foundational postulates are very much unchanged. Now, it's often said that quantum mechanics describes it's the physics of the very small. Now, that's not quite true. In reality, quantum mechanics describes all matter, from the very large to the very small. A better way to put it is that quantum mechanics is only visible at small length scales of about 1 nanometer or 1 billionth of a meter. So, an analogy would be a computer screen. If we look at a computer screen, we simply see an image. That's all we can see. But if we were to zoom in on the computer screen very close, then we could see individual pixels of red and green and blue. And if we zoom back out again, we would again see just an image. We could not see the pixels. In the same way, the microscopic constituents of everyday matter, things like elephants, even pinheads, they obey quantum mechanical laws at the microscopic level. But when we zoom out, when we look at very large length scales, like everyday objects, then we can't tell that they're quantum mechanical. Everything looks classical in nature. But even though quantum mechanics is only visible at small length scales, it's incredibly important. For instance, without quantum mechanics, many biological reactions would not even occur. In fact, chemical bonding itself would be impossible, so that molecules wouldn't exist. In fact, even atoms would be unstable, so the universe as we know it would not exist, and what's worst of all, I would not have a PhD. And of course, that makes very little difference to most of you. But all I'm saying here is that for the universe to even exist as we know it, quantum mechanics is extremely important. Okay, well then what is quantum mechanics? Let's talk about some of the postulates of quantum mechanics. And I've listed 3 here. You might be able to list more, but I've tried to simplify them as much as possible. Let's go through each of them in turn and talk about some of their implications. Postulate number 1. All information about a particle is provided by the wave function associated with that particle. You can ignore the math on most of these slides. I'm going to talk you through their implications. A wave function is simply a function like any other function. For instance, we could plot the temperature in Durham, North Carolina as a function of the time of day. In the same way, a wave function plots the probability of observing a particle at a given point in space as a function of the position of the particle in space. So for instance, the wave function of a particle says there's a 1% chance of finding the particle here, there's a 5% chance of finding it here, there's a 4% chance of finding it here, and so forth. Now, what are some of the implications of this first postulate? Well, number 1, most quantum particles are delocalized, meaning they do not have a well-specified position. In classical mechanics, every particle has a well-defined position. For instance, there's a little sign associated with every particle that says the particle is here in space, at one given position. On the other hand, most quantum mechanical particles are delocalized. Although we can say is with some high probability the particle is somewhere in some given region of space. We can't pin it down to a specific location. A second implication is something known as the Heisenberg uncertainty principle. In classical mechanics, every particle can be assigned a specific position and momentum. We can know both the position of the particle and the momentum with infinite precision. For instance, I can say if I have a classical baseball, it is right here in front of me, and it is moving at 10 meters per second towards my face, for instance. And I can know both of those quantities exactly. On the other hand, a quantum particle can only be assigned a position and momentum within some degree of uncertainty. I cannot know both position and the momentum of a quantum particle exactly at the same moment in time. This is not a limitation of our measurement device. No matter how precise our measurement device is, there's a foundational fundamental limit to how exactly we can know its position and momentum simultaneously. Third, a quantum mechanical particle can be put into what's called a superposition state. For instance, imagine a classical elephant. A classical elephant might be in 2 valid states. It could be either gray or it could be multicolored. Now, a quantum mechanical elephant could be in the state gray, or it could be in the state multicolored, but it could also be in what's called a superposition state. It could be both gray and multicolored at the same time. That's very strange and unintuitive, but that's what quantum mechanics tells us. Now, what's postulate number 2? Postulate number 2 is that the motion of of quantum mechanical particles is governed by the Schrodinger equation. That's not Newton's equation of motion, but the Schrodinger equation. Again, you can ignore the math here. These are some expressions of the Schrodinger equation. But what are the implications of the fact that quantum mechanical particles are governed by the Schrodinger equation? Let me list a few. Implication number one. A quantum mechanical particle can tunnel through barriers rather than going over them. Imagine I have a classical soccer ball and I give it a kick. If I do not give it enough of a kick to go over the hill, the ball will simply roll back down the hill again because it does not have enough energy to climb the hill. On the other hand, if I kick a quantum mechanical soccer ball, I do not give it enough energy to go over the hill, but nonetheless it could disappear from one side of the hill and reappear on the other side of the hill, even though it does not have sufficient energy to go over that hill. Now this is an extremely strange phenomenon, and yet it is the basis for the scanning tunneling electron microscope. Without this property of quantum mechanical particles, STEMs would not even exist, and they are found all over the world today. They form a major instrumentation device in most semiconductor physics laboratories. Okay, what's the second implication of this postulate? Well, this postulate says that quantum mechanical particles can take all paths at the same time. Imagine I have a classical mouse. That mouse will take a single well-specified path or trajectory as a function of time. It'll travel through the maze in a given well-specified path to find the piece of cheese at the end of the maze. On the other hand, a quantum mechanical mouse will effectively take all possible paths to the cheese, even crazy ones. Now granted, there's a very small probability or amplitude associated with each of the crazy paths, but nonetheless there is a contribution from each of these really crazy, unintuitive, non-classical paths. They all contribute to the final probability of the mouse finding that piece of cheese at the end of the maze. Okay, in some ways, this third postulate of quantum mechanics is the most unintuitive and astounding of all. It's a little bit hard to formulate in language. It's easier to present mathematically, but I'm going to try to explain it to you. This postulate says that measurement of any quantum mechanical system, like a particle, is associated with an object called an operator. This is simply a mathematical object. Now, what are the implications of this postulate? Well, implication number one. If I have a classical mechanical elephant, and the elephant is gray before measurement, I know that it is gray. If I measure the color of the elephant, then I can be absolutely certain that I will measure the elephant as being gray. In other words, if I know the state of the elephant before measurement, then the effect of the measurement, in other words, the outcome, I will know deterministically. I will know with 100% certainty what the outcome will be. On the other hand, the outcome of measurement in quantum mechanics is inherently probabilistic. What does that mean? Well, let's say I have an elephant in the multicolored and gray state at the same time. It's in the superposition state. If I know with 100% certainty the elephant is in that state, and I ask you, what is going to be the outcome of measuring the color of the elephant? All you can say is, well, 50% of the time you will observe the multicolored state, and 50% of the time you will observe the gray state. But the outcome of the measurement is intrinsically probabilistic. What's a second implication of this postulate? Well, measurement necessarily alters the state of the observed system. Again, let's take our elephant. If the elephant is gray before measurement, then after I measure the elephant, it will still be in the state gray. That's not true of the quantum mechanical elephant. Imagine the quantum mechanical elephant is in the state multicolored plus gray at the same time. After the measurement, let's say I observe the state multicolored. Well, now the state of the elephant has changed. Before measurement, it was in the superposition state, but after the measurement, it is not anymore. The measurement necessarily alters the state of the observed system. And again, this has nothing to do with the precision of our measurement device. No matter how precise and how delicate our measurement device is, this is a fundamental property of quantum mechanical systems and measurements. And finally, I'm going to skip the details here, but because this is quite philosophical and a little bit complicated. But properties in quantum mechanics are actions to be performed, not labels to be read. What does that mean? Well, when we think about things in terms of classical mechanics, we think about the properties like position, color, size, as almost being like little labels that are affixed to every object in the universe. And what the scientist does is he measures the position or the color of the size of the object simply by reading off the attributes listed on those little labels. On the other hand, in quantum mechanics, properties function more as actions. In other words, they're verbs, things that be performed on a system, rather than just as labels to be read off of a system. So, for instance, if I want to measure the position of a quantum state, it's like having a box labeled position with a little readout. I put the state into this position measuring device, and the little readout says, oh, the elephant is here, or the elephant is gray. But the object itself does not have a specified property independent of measurement. That is, there's a caveat there, unless you're a neo-realist. We'll talk about this in a second. But again, this is a very dramatic and remarkable consequence of quantum mechanics. We'll talk about the implications in a little bit. Okay, so I hope you've seen that the implications of quantum mechanics, some of the fundamental ideas that flow from these postulates are incredibly strange. I recall people laughing when I've given this talk previously because they just cannot believe this is what quantum mechanics says about the universe. Now, I'm going to, unfortunately, for lack of time, skip the section on quantum weirdness in action. In other words, I had a couple of experiments that really clearly demonstrate how bizarre and unintuitive quantum mechanics actually is, and how you could see those effects in actual experiments. But as I've said before, quantum mechanics has been verified to a greater degree than any physical theory, perhaps in all of human history. There is no scientist or physicist that I know of at an academic university that would believe quantum mechanics is false. They all have different interpretations of quantum mechanics, but again, it's remarkably well established as a scientific theory. So let's skip this section. If you're interested, you can look online, and my slides are there. But let's skip ahead to the interpretation of quantum mechanics, section 5. I want to list three major interpretations of quantum mechanics. I want to stress here that these three interpretations are neither confirmed nor disconfirmed by any known experiment. Indeed, we can't even think about potential experiments that might confirm or disconfirm these interpretations. So we cannot appeal to experimental evidence to say which interpretation is correct. Rather, we'll have to settle which one we think is likely to be correct based on philosophical or metaphysical reasoning. Again, they give the same predictions for every known experiment that we have or that we can even imagine having. So what is the fundamental question that's being addressed by each of these interpretations? The question is this. Quantum mechanics tells me that reality is really bizarre. It's composed of wave functions and these elephants in these multiple superposition states at the same time. It's just, I've never seen anything like it. And yet, if I look out the window, all I ever see are gray elephants and anvils and baseballs with specified positions and momenta. So the question is, why does reality look so normal to us when quantum mechanics says it actually is so bizarre and unintuitive? That's the question with which all of these interpretations are grappling. So let's consider each of these interpretations in turn. I'm going to list three. There are more, and there are all subtle variations, I think, of these three, but these are the three major ones. The first is called the Copenhagen interpretation. And this interpretation, it solves the problem of why reality looks so normal, even though it's at root quantum mechanical in nature. It solves this problem by saying that measurement collapses the wave function. In other words, reality does exist as this weird, unintuitive wave function. But when I measure it, when I perform a measurement on a system, that collapses the wave function of the system so that I see only particles. I observe only particles with distinct and intuitive properties. And here's a good quote. Observations not only disturb what is to be measured, they produce it. So the action of measurement actually produces this particle-like nature that we observe in day-to-day life. Okay, so what are the pros and cons of this interpretation? Well, it is the orthodox or traditional interpretation. It's been around for a long time, and if you take a first-year graduate course in quantum mechanics, it is the interpretation you're likely to see explained. But there's some major downsides. Number one, and this is the obvious one, what exactly is a measurement device? I mean, we just said that the whole universe is quantum mechanical, but when I measure it with a measurement device, it suddenly looks classical. In other words, the measurement device collapses the wave function so that it looks more or less classical. The question then is, well, what's a measurement device? And if everything in the universe is quantum mechanical, well, why does this measurement device behave so differently than the rest of the universe? And here's the difficulty. If you really push on a proponent of the Copenhagen interpretation and really press him and say, well, what exactly is a measurement device? There's really, I think, this is my opinion, the most consistent stopping point at which you can say, well, this is what collapses the wave function, is to say that somehow measurement is related to consciousness. Now, whether that's human consciousness, whether or not cats and dogs and bacteria can collapse the wave function, it's unclear. But again, the majority of physicists actually tend to punt this question to the philosophy department. This is why most modern physicists do not ask these difficult and metaphysical questions about the nature of a measurement device. But again, this is seen as a major shortcoming of the Copenhagen interpretation. That it seems like one of the most consistent stopping places is to say that somehow measurement is associated with consciousness. That rubs a lot of physicists the wrong way. Okay, so if we don't like the Copenhagen interpretation, what other interpretations are available to us? Well, here's a second one. This is known as the Neo-realist interpretation, and it was favored by Albert Einstein. Now, we talked before about how under the Copenhagen interpretation of quantum mechanics, objects do not have properties independent of measurement. Now, that sounds like a sort of abstruse philosophical claim, but to show you how radical it actually is, let me tell you an anecdote about that's recorded by Albert Peiss, who's a physicist himself, and who wrote a biography of Albert Einstein. One day, Peiss and Einstein were walking together, and they were talking about quantum mechanics, and Einstein suddenly turned to Peiss and said, "Do you really believe that the moon exists only when you're looking at it?" Now, rather than simply saying, "Oh, come on, Albert, of course the moon's there when we're not looking at it. Of course it exists." Now Peiss did not respond that way. Instead, they spent the rest of the walk talking about what it means to exist. Now, this is exactly the difficulty that made quantum mechanics, and specifically the Copenhagen interpretation, so distasteful to Einstein. He did not like the idea that properties do not exist independent of measurement, which is the view taken by the Copenhagen interpretation. So he and others have adopted what's called the Neo-realist interpretation, which aims to preserve this classical intuition that properties do exist, that particles do have properties independent of measurement. So what are the good things about the Neo-realist interpretation? Well, it retains what's known as metaphysical realism. In other words, particles really do exist independent of measurement, and they have properties independent of measurement. What are the downsides? Well, there's a major cost here, and I'm going to tip my hand, I think, a little bit. In order to hold to neo-realism, you have to believe that there are undetectable pilot waves that bounce around the universe, traveling faster than the speed of light, effectively propagating backwards in time, that make everything appear classical in nature, even though it really is quantum mechanical in nature. Now, again, that's a little pejorative, but this is why the majority of physicists no longer believe in the neo-realist interpretation of quantum mechanics. It strikes most physicists as being a tremendously ad hoc explanation. In other words, you're really just trying to preserve your classical intuition about reality by postulating these entities that you can't detect, that travel faster than the speed of light, that are invisible, non-measurable, etc. Again, that strikes most people as very ad hoc, which is why this interpretation has really fallen out of favor. Okay, but if we don't like Copenhagen and we don't like neo-realism, well, what's left? And the answer is the many worlds interpretation. What this interpretation says is that there is no wave function collapse, so there is no measurement problem. What happens is everything in the entire universe is quantum mechanical. But when I have a scientist, let's say this little scientist is inside the universe, and everything is quantum mechanical, and he measures this quantum mechanical coin that's in the state H plus T, heads plus tails. He measures that coin. At that moment of measurement, the universe bifurcates or splits. So now we have a multiverse, and there are two branches of the multiverse. In one branch of the multiverse, the coin is in the state heads, and the scientist thinks to himself, oh, the measurement came up heads. But in the other branch of the multiverse, the coin is in the state tails, And the scientist thinks to himself, oh, the coin came up tails. So any time any measurement is made anywhere in the universe, and indeed, anytime any two particles interact anywhere in the universe effectively splits into multiple branches, and in each of the branches of the multiverse, the different outcomes of the measurement are observed. Now, what are the pros of this interpretation? Well, it's uniform. There is no wave function collapse, and there's no measurement problem because there's no measurement device. Everything is treated on the same footing. Everything is just quantum mechanical in nature. But there's a major downside, and I guess you've probably already seen it, which is that we have to postulate the existence of an infinite number, or essentially infinite number, of undetectable, non-measurable, even in principle, alternate universes that we can't see. They're all there, but we will never be able to detect them. And if you think about it, this actually removes the possibility of us knowing anything about the real universe, because the real universe is actually the multiverse, and all we are is this tiny, tiny little branch of the multiverse, and we can only see within that little branch. And there are other problems with the many worlds interpretation, but again, that's the third major school of interpretation of quantum mechanics. And at this point, you might ask, well, which is the right interpretation? I mean, all of these sound pretty bad. Well, exactly, that's the point. If we had an interpretation that fit all of our physical data and with which we were completely familiar and fit everything that we know, well, the problem would be solved. But the point is, there isn't an interpretation like that. There isn't an interpretation that is favored by all physicists that resolves all of our problems. This is why they're all on the table still. Okay, so in this last section, I'd like to talk about some of the philosophical implications of quantum mechanics. Let me discuss 5, and then I'll return to the questions we asked at the very beginning with which we were framing our discussion. So first of all, quantum mechanics implies that almost no event is strictly impossible. Okay, let me give you an example. If classical mechanics were true, and I put an apple on a table, and I say, what's the probability that the apple will teleport through the table and end up on the floor? Your answer can be 0. There is a 100% chance the apple will stay on the table where I put it, in a second from now. But because the universe is quantum mechanical in nature, and if I ask you, what's the probability the apple will teleport through the table and end up underneath the table, a second from now? Your answer is, well, it's very, 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 very improbable. It's not impossible, strictly speaking. It's just very, very, very unlikely. Now, to show you that I'm not exaggerating, let me give you a quote that was from the New York Times a few years ago. I'm really glad I found it. The reporter was interviewing a physicist who works at the LHC, that's a particle collider over in Europe. And he was asked whether the particle collider will create a huge explosion that would destroy the entire world. And the physicist said, well, no, I don't think it will. But, he said, quote, the random nature of quantum physics means that there is always a minuscule, but non-zero, chance of anything occurring, including that the new collider could spit out man-eating dragons. That's what he said. Now, he's joking, sort of. But technically speaking, that's exactly what quantum mechanics says. Nothing is strictly impossible, just very, very, very improbable. A second, quantum mechanics fiddles with the notion of strict determinism and causality, and possibly with even determinism with regard to human freedom or free agency. So, for instance, in classical mechanics, in classical physics, we have a well-defined series of causes and effects. So imagine you have a line of dominoes, one falls, the next one falls, the next one falls, and then the final one falls. You have a series of causes that lead deterministically to some effect, which the scientists say measures at the end. And for instance, Macbeth has some dream, and it leads to a series of events in which he's crowned king, then eventually he dies. You could say, well, it's all deterministic. The laws of nature are deterministic. They're completely causal in nature. There's no room, as it were, for human freedom. However, quantum mechanics does seem to fiddle with notions of causality and, in particular, determinism. So for instance, imagine we have a quantum coin, again, in the state heads plus tails at the same time. It's in the superposition state. If I measure the coin and I observe it to be in the heads state, the question is, well, that's the effect, but what's the cause? And the answer is not clear. Suddenly, our notions of causality have gotten fuzzy. So maybe Macbeth has this dream, this vision, and then he becomes a pizza delivery man. We just don't know whether there's a strict sequence of cause and effect that's deterministic in nature. Now, I'm not saying that this implies somehow human freedom is necessarily true, but I'm saying it seems to allow for the possibility of human freedom and non-determinism in a way that even could be somehow causal, and that somehow we could influence uh, actions in the material universe. It's not clear that is true, but it seems to leave the room for the possibility that is true. Whereas classical mechanics makes that less likely or less plausible. It fits less well into a classical mechanical scheme. Third, we talked about how within the Copenhagen interpretation, consciousness seems to play a distinct role. I can go into this in more detail, but I won't. I want to leave you just with a few quotes. Um, several Nobel laureate physicists who were the founders of quantum mechanics, Eugene Wigner, John von Neumann is another one, but they would actually go further and say that quantum mechanics implies that dualism is true. In other words, it implies that mind has a distinct role from matter in the universe. Now, I wouldn't go that far, even if Copenhagen is the true interpretation of quantum mechanics. But I would say that it's very suggestive. Quantum mechanics certainly suggests that consciousness somehow plays a unique role in the universe, even, by the way, within the many worlds interpretation, and that's beyond the scope of this talk. But here's a quote from Nobel laureate Eugene Wigner himself, one of the founders of quantum mechanics. He said, "It follows that the being with a consciousness must have a different role in quantum mechanics than the inanimate object." That was his opinion. And again, I wouldn't go that far, but certainly I would say that quantum mechanics is suggestive that consciousness does somehow play a distinct role in the universe. Fourth, this idea that quantum mechanics says that there are inaccessible realities that cannot be observed by the scientist. They're simply off limits. And in fact, the entire field of quantum cryptography is predicated on the idea that the wave function itself is not directly measurable by observers. And again, so quantum cryptography, this whole field would not exist if not for this fact that the wave function is this intangible, immaterial, inaccessible reality to which we will never be able to directly have access. But finally, I think one of the main lessons of quantum mechanics is that the nature does not follow our intuitions. Nature does not ask us how it ought to behave. It is the way it is, and we have to just keep an open mind when we approach nature in reality in a larger sense. There's a really funny exchange. It's probably apocryphal, but between Albert Einstein and Niels Bohr. Talking about quantum mechanics, Albert Einstein said once, he couldn't believe it because he said, "God does not play dice with the universe." That's the origin of his famous quote. He was talking about quantum mechanics and he said, "God does not play dice with the universe." Now, in response, Niels Bohr is reported to have said, "Albert, stop telling God what to do with his dice." And that's the point. We are not allowed to dictate to nature what it's supposed to be like. And here's how Richard Feynman, who's a famous physicist from Caltech, here's how he put it. He said, "Do not keep saying to yourself, if you can possibly avoid it, but how can it possibly be like that? Nobody knows how it can be like that. But it is like that." That's his point. And so again, we have to just keep an open mind as scientists, as humans, and simply ask reality and ask questions about reality rather than dictating terms to reality. I think that's one of the most important lessons that you can learn from thinking about quantum mechanics. Okay, so let's go back to those initial assumptions that I listed. These are the fundamental presuppositions that are necessary in order to even do science. Things like, well, we have to assume the universe is rational, that we can understand it, the universe is regular, that it obeys laws of cause and effect, there are explanations to phenomenon, etc., etc. Now, what does quantum mechanics have to say about these fundamental assumptions? And I would say it makes things very complicated. And when you start talking about quantum mechanics, things like, well, is the universe really rational? I mean, we're really pushing the bounds of what we can understand as human beings to some degree, or we seem to be. What about this idea that there are an infinite number of undetectable parallel universes? I mean, talk about violating Occam's razor. This is the principle that says that the simplest explanation is most likely to be the correct one. I mean, if the many worlds interpretation doesn't violate Occam's razor, I don't know what does. I mean, according to many worlds, there is a universe in which I am 100 feet tall with machine guns for arms. There is a universe in which unicorns exist. These universes exist. There are other branches of the multiverse. But if that hypothesis does not violate Occam's razor, then I don't know what does. And again, there are these fundamental assumptions like causality, uniformity, metaphysical realism that are really challenged by quantum mechanics. And again, these are assumptions that we thought were just foundational to the scientific endeavor, and yet I think quantum mechanics does make things complicated. But finally, let's look at some of the naive assumptions we might have made about the nature of reality. So, for instance, things like, well, the laws of physics state that miracles are impossible. If God exists, well, he couldn't intervene in the natural world because he'd have to violate natural laws, etc., etc. Now, what does quantum mechanics have to say about these naive assumptions that might nonetheless be familiar and even widespread among naturalists? And I would say, again, quantum mechanics make things very complicated. Uh, are miracles, strictly speaking, impossible? No, not according to quantum mechanics. Nothing is strictly impossible. Things are just very, very, very unlikely. If God does exist, then he wouldn't have to break the laws of nature in order to intervene in the natural world, simply because the nature does not rule anything to be, strictly speaking, impossible. A third, well, is consciousness or mind, is it distinct from matter? Is there a separate property of reality called mind? Well, if you adopt the Copenhagen interpretation and follow it through to what I think is the logical conclusion, the answer seems to be yes. And even within the many worlds interpretation, if you want to say, well, no, everything is quantum mechanical, you still have to do some fiddling to get it to be consistent with what's called materialism, a materialistic view of the mind. So suffice it to say that, again, quantum mechanics challenges this idea, this naive idea that mind just can't be a distinct entity from matter. Again, quantum mechanics says there might be a distinct category called mind, which has a physical, or sorry, that is not simply reducible to physics, or sorry, reducible to matter. And finally, the idea that the universe does not contain hidden or unknowable realities, well, that's just false. Again, as we've seen, quantum cryptography is an entire field of study that is predicated upon the idea that there are hidden and unknowable, inaccessible realities, that is the wave function, that we cannot measure directly. That last idea is just false. So, some concluding quotes. As I've said, no one, at least that I know, and certainly no one that I've ever encountered, doubts quantum mechanics. It has been confirmed with a precision that is unprecedented in the history of science. This is a quote from Merman, saying that this kind of precision in verification has never been before achieved. And yet, you have people like Einstein and Schrodinger himself saying that it's just so radically unintuitive, it's really troubling. Schrodinger himself said he wished he'd never had anything to do with it. So I hope you don't feel that way, even after this talk. I hope that I have motivated you to see quantum mechanics as something that's very beautiful, very fascinating, and I hope that it does challenge your assumptions about the nature of reality, because it should. It should. So in conclusion, let me thank my wife, Dr. Christina Shenvy, my advisors, past and present, and finally Duke InterVarsity Fellowship for allowing me to give this talk, and thank you all for listening. Bye.